In this video, I'm going to discuss the idea of superposition in quantum mechanics. Superposition is the adding of two different waves to create a kind of combination wave through either constructive or destructive interference. So the example we're going to use is the free particle where the potential function is 0. We're going to use one dimension so that it only has x derivatives in there for the momentum or potential energy terms. So for the free particle, the Hamiltonian is the momentum in the x direction squared divided by 2m. And so using the fact that the momentum operator is h bar over I times the first derivative of x, while doing the first derivative twice gives you the second derivative. So that's the Hamiltonian operator. This will be the combination wave function, the superposition of two wave functions psi 1 and psi 2. And psi 1's function is going to be e to the ikx, which is a complex function. And we're going to make the second one e to the minus I times 2kx. It could be anything as long as it's different. Okay, so the first thing to realize is that these individual psi 1 and psi 2 obey the Schrodinger equation, the time-independent Schrodinger equation. However, this will not, okay? And the reason being is that if you apply the Hamiltonian to this function, you get two possible answers and they'll be combined and mixed up. The other thing you have to be aware of is that for some problems, we cannot integrate psi squared to give a probability distribution that integrates to 1. And so the easiest way to consider those is to actually make the coefficients carry the normalization condition. That is to say, when we square the coefficients, they should add to 1. And the magnitude of the square of the coefficient tells you something about the probability of finding the particle with one particular eigenvalue or another. Okay, so let's go ahead and work out this example. First of all, let's find out what the eigenvalues are for psi 1 and psi 2. All right, so h is minus h bar squared over 2m. And second derivative. And we're going to apply this to psi 1 first. And so now I'm going to leave out the 1/2. And I'll show you why in just a second. Okay, so the first derivative e to the ikx is going to be ik times e to the ikx. All right, and then, all right, I can't do it that way. Got to remember the stupid order in these things, and I'm running out of room. All right, so let's try to crowd this all in here. Write the constants first, minus h bar squared over 2m. Then ik, and then the first derivative of e to the ikx. Okay, so this whole term here is the first derivative of e to the ikx. Now we take the derivative of e to the ikx again, and we get ik again. Okay, now I squared is minus 1, so we're going to get a positive h bar squared k squared over 2m times the original function, e to the ikx. Okay, so psi 1 is an eigenfunction of the Hamiltonian with an eigenvalue of h bar squared k squared over 2m. Okay, so now if we were to do exactly the same sort of thing for this guy, you should first of all realize that instead of getting ik, you're going to get I times 2k. All right, and so minus h bar squared over 2m times the second derivative of e to the minus I 2kx. That's psi 2. We're going to get minus I2k squared, because we're going to take the derivative twice, times the original function, e to the minus I2k x, and then this minus h bar squared over 2m. And so e to the minus I2kx is also an eigenfunction of the Hamiltonian here with a different eigenvalue, though. Okay, and it's going to be 4 h bar squared k squared over 2m e to the minus I2kx. Okay, so now what about the 1/2 and the minus square root 3 halves? Okay, well, I can just multiply both sides of this equation here by 1/2. Just put that 1/2 in here and 1/2 here. And in the end, that 1/2 will be over here. And then, of course, this would be the psi 1 containing the normalization factor. Okay, so this is one of the things that you have to understand, that if anything's an eigenfunction of an operator, then a constant times that function is also an eigenfunction of the operator. So in principle, there's an infinite number. However, we want to choose constants times our eigenfunctions specifically to create a normalization condition. That is to say, we want to choose coefficients where the sums of the squares equal 1. So let's go ahead and square these guys. See, I'll call this C1. 1/2 squared is 1/4. And this coefficient, C2 squared, and the reason I use these vertical bars, it could be a complex number. You have to know how to square those. And so this second coefficient, when we square it, now notice the sign doesn't affect the square of the coefficient, so it won't affect the probability. However, the sign is very important for the way the two waves add or subtract, right? This would be subtracting this wave from that wave, whereas a plus sign would be adding this wave to that wave. So one would probably have more constructive interference and the other have more destructive interference. Okay, so now you could actually put this whole thing into the equation and do h psi